we looked at why we want to do it, right? It's about the omitted variable bias issue. So we want to collect the variable that can be omitted and include it. We also know how to interpret the coefficient, right? So holding everything else fixed means really something, right? That's very important. And we also do how to do the estimation, like this matrix, inverting a matrix is very convenient tool. And we also kind of know what to avoid in terms of perfect multicollinearity, how to use more than one dummy variables, things like that, right? So that's chapter 6. In chapter 7, we are going to do the inference. Inference means testing and confidence interval, okay, when you have a multiple regression. So today I plan to do chapter 7.1 and 7.2. There is nothing new in 7.1. It's just very simple. It's just repetition of chapter 5. So in chapter 5, we have hypothesis like this. Is beta 1 equal to 0? That's a null hypothesis. And we have seen this kind of hypothesis a lot before. The only difference is there is additional independent variable x2 in the model. What about testing? Is there any difference? Answer is no. Everything remains the same. Confidence interval. Any difference? Answer is no. Okay? Just like chapter 5. So how to do a test? So we have same step, 4 steps, right? So we first want to calculate beta 1 hat. We also calculate the standard error of the beta 1 hat. Right? So how do you do that? So R produce the outcome. Beta hat, standard errors are there. Step 2, we calculate T statistics, which is beta 1 hat minus the value of the beta 1 under the null. So null says beta 1 is equal to 0, so we are going to use 0. But if null says beta 1 is equal to minus 1, then you have to use minus 1 here. Beta 1 hat minus minus 1. If null says beta 1 is equal to 100, then you want to say beta 1 hat minus 100. The beta 1 under the null. So that goes into here. And then we want to divide it by standard error. The next step is to get p-value, which is 2 times probability that your actual t-value is bigger than, the t-value is a random variable, is bigger than your actual t-value. And last step is decision. Reject the null if p-value is less than alpha, right? And if you want to use t-value, for example, suppose that alpha is 0.05, then we reject the null if t-value is bigger than 2 or less than minus 2. So essentially, We are comparing the size of beta 1 hat against its standard error. Standard error is the variability of beta 1 hat. What is the beta 1 hat if I have another sample? Is it going to be very different from the beta 1 hat from my sample? If that's the answer, then you cannot believe that the answer is very conclusive from your answer. Beta 1 hat is much bigger than the uncertainty, then you can say this. Even if I do another sample, then my beta 1 hat is not going to be too different from my current beta 1 hat, so that I can confidently reject the null hypothesis. Okay? So that's a decision. Again, there's no difference in a confidence interval. This is how you get it, right? Beta 1 hat plus minus 2 times standard error. So everything is perfectly the same as in chapter 5. Okay, so let's move on. What about 7.2? So what do I mean by a join hypothesis? Just one example. So the difference is now we have 1 and 2 restrictions, okay? Just one example. By the way, another way to say this is they mean the same thing, okay? Second example. Again, this is a joint hypothesis. You can make a lot of joint hypotheses. Third example. I just make it up. But again, this is one example of a joint hypothesis. So what is common in all these examples? You have more than one restrictions. Okay, so that's the key. So let's define this quantity Q. That is the number of restrictions under the null hypothesis. Now we have 2 restrictions. So Q is equal to 2. We have 1 and 2 restrictions. And by the way, they're connected by this AND, okay? So this has to be true, and this has to be true. So Q is equal to 2. How many restrictions we have? We have 2 restrictions, okay? So they are all examples of a joint hypothesis. So the chapter 7.2 discuss how to do a joint hypothesis test. So let's just focus on this example. First of all, how to do it? Let me suggest 2 methods. One is, so maybe I can say a sequential t-test. So this is what I mean. You apply a t-test for this single hypothesis, How do you do it? You just calculate t-value for beta 1 hat and decide whether you want to reject it or not. Now you apply another t-test based on this t-value, and then you decide whether you reject it or not, just based on t-test. Goes like that, okay? So when you reject the joint hypothesis, or that's harder. So when you fail to reject the joint hypothesis, that's when you don't reject this hypothesis and you don't reject this hypothesis. That's when you don't reject a joint hypothesis. Sounds kind of plausible, right? Do you want to do it? It's very intuitive. We already know how to apply a t-test, so why not do it twice, independently? Answer is, this is wrong. So don't do it. And instead, we want to use something new, which is the F-test, okay? So we got to do this. So let me just tell you the difference between a t-test and an f-test. So t-test is something we already know, and f-test is kind of new. So when to apply an f-test? It is when q is bigger than 2 or equal to 2. When to apply a t-test? It's when q is equal to 1. Okay, so that's the difference. So for example, a hypothesis like that has two restrictions. Q is 2, right? So you have to apply an f-test. You can apply t-test many times. But if the hypothesis is like this, like in chapter 7.1, q is equal to 1, right? So that's why you want to use a t-test. The key is the number of restrictions under the null. So side note, you can apply an f-test when q is equal to 1, 2. So f-test is like, it can handle any cases. Generalist. T-test is something like a specialist. Okay? When q is equal to 1, you can either use this or that, and the conclusion must be the same if you do it right. What do I mean by they have the same conclusion? The p-value of this t-test should be exactly equal to the p-value of this f-test if q is 1, okay? So I'll explain later why that is the case. You know, when I explain this, I chose not to say that we want to reject the null hypothesis. Can you guess why? I didn't want to talk about that. I instead say, fail to reject the null hypothesis. What's the difference? For a simple hypothesis, they are about the same thing. Not the same thing, but one is not more complicated than the other. But for the joint hypothesis, rejecting the null is a lot messier than fail to reject the null. Because once you reject the null, you have to think about the alternative, right? So what is the alternative hypothesis of this one? Can you write it down? So suppose that this is your null hypothesis. Alternative is anything that is not true under the null. So can you write down the alternative hypothesis of this case? For a simple hypothesis, it's very simple. Beta 1 is just meaningful. But what about this? So why I was afraid of saying rejecting the null? It's because it's kind of messy. It includes many different possibilities. Can you write it down? So what can be the alternative hypothesis of something like this? What is the opposite of something like this? So what can happen if this is false? What can happen if you reject this? What does it mean? So under the null, x1 is useless and x2 is useless in the regression. It has to be dropped. Right? So what's the opposite? Is it the opposite? If it is not, why? If you reject this, does it necessarily mean this? No, right? Because there are more cases, right? What is the other cases? Beta 1 is 0. What happened to beta 2? Are they all? If you reject this, does it mean that it's one of these two cases? No, right? There's even more. So what is out there? Beta 1. So we have at least 3 different possibilities. If you reject this, and we don't know which is the case, the test does not tell you. Okay. By the way, when this happens, this cannot happen at the same time. So you have to connect them by OR, right? You cannot connect them by AND. Because they're mutually exclusive. So if you reject this, it means either one of these 3 possibilities is true. But we never know which one is. Okay, so how the F-test look like? I said use an F-test. The question is how. And try a few times. Okay, this is just an example. When Q is equal to 2, and when you happen to have this null hypothesis. F looks like is how an F statistics look like. So what is T1? It's the T value for beta 1. What is T2? It's T value for beta 2. So you have to know them. Well, you have to know more. You have to know the correlation between T1 and T2. Okay? So this guy is a random variable because beta 1 hat is a random variable. This guy is a random variable. So you can think about the covariance and correlation coefficient, right? So if you figure out this correlation coefficient, then you can calculate the F statistics, which is not really easy. So let's try to understand it, okay? So assume that, although this is usually not the case, the correlation is equal to 0. Then F value can be simplified So I simply assume that this part just disappears. So it goes away, this part goes away, so denominator is 1. So in the simplest case, an F statistics look like this. Okay? Now think about this. When you reject a simple hypothesis, we have some intuitive idea, right? When t is bigger than 2 or less than minus 2. So that's when t1 squared is bigger than 4. Now you can apply the same idea to t2 squared. So if bigger than 4, or if this is bigger than 4, then at least one coefficient is significant. So that's kind of our intuition. So it's going to be like approximately 8, right? If you sum them up. And you divide by 2, because the number of restrictions is 2. So approximately, if the F value is bigger than 4, means that you can reject something. I mean, this is not an exact of anything, but just an intuition, because F statistics usually look like this. So F being 4 becomes some kind of boundary cutoff of being significant. Does it make sense? Now, let's be more serious about this rejecting the null or not rejecting the null thing. You know, so we know that t value is bigger than something is significant only because we know it's going to be approximately a standard normal distribution. And if it is in this area, that's kind of very unlikely event, right? So in that sense, we can think about this testing because we know the distribution of our statistics. So t statistics, some kind of, if the sample size grows bigger and bigger, follows a normal distribution. Right? So normal is our reference. As a normal distribution bigger than 2 is very unusual event. That's why we reject. What about F? Do we have something like this? Yes, we do. And that's an F distribution. So let me just remind you that an F distribution from your statistics is looking like that. It has 2 degrees of freedom. The denominator, you have a chi-squared random variable with q degrees of freedom. And you normalize it by dividing it by the degrees of freedom itself. Okay? And the denominator, you have another chi-square distribution with m degrees of freedom, and you normalize it by dividing by the degrees of freedom. And suppose that they're independent. Then in statistics, we kind of show or argue or insist that we call it a F distribution. So F distribution is a ratio of 2 chi-square distribution. Now, what is F, Q, and infinity? That's F, Q, and M when M is very big. Okay, so that's the meaning of F, Q, and infinity. Infinity is actually not a degrees of freedom. It just represents the case where the degrees of freedom in the denominator is big enough, like bigger than 100, even bigger. So that's what it is. And the F statistics over there essentially follows FQN infinity distribution, which looks like this. And F distribution looks like this, okay? It cannot be minus because it's a ratio of two positive numbers. Chi-squared only takes positive values, right? So that's why it takes values only on this area. Now for a normal distribution, an extreme event means two different things. Extreme in the positive, extreme in the negative. For an F distribution, there is only one kind of extreme cases, only over there. Because think about this. When T1 and T2 are very small, looking very normal, F is going to be very small. When one of them is looking abnormal, taking big value, then it only increases F statistics on the positive way. It never goes to the other way because you're going to square it. Okay? So the being abnormal for the F distribution looks this right tail. So when you have alpha, you assign the whole probability to the right tail. But for the t-test, you assign only half of it, right? So when you calculate a p-value, you calculate the probability that if I draw another sample and calculate my F statistics, what is the chance that it is more extreme than my actual F statistics? Okay, so you're looking to the right tail. Let me just mention one thing. Do you have to memorize this? Answer is no. Okay? So next time I'm going to show how to use an R function to calculate a F statistics. So previously I said we shouldn't use a sequential t-test for a joint hypothesis, right? So let's try to understand it. The thing is, it's extremely tricky. So I'm going to do some calculations, but I usually get confused, okay? So I got to be really careful to not to make any mistakes. So the short answer is, so what's the problem? The problem is we cannot have the right or correct size because the size of such test is wrong. Let me remind you, the size is the probability of rejecting a null hypothesis if, what is the size? If the null is false. Is it correct? No, reject the null. No. I got confused. It's really kind of tricky already. If null is false, then we want to reject it, right? So it's not a problem. Null is true. When null is true, we don't want to reject it. If you reject it, that's a mistake, right? The size is the probability of this mistake. And somehow, we have to argue that this does not go right if you use a sequential t-test. So let's try to understand why. So listen carefully. I may get confused again, but correct me, okay? Now what do I mean by applying a t-test for this hypothesis? If you view it as a simple hypothesis. So it's going to be something like we calculate the t-value and we reject this hypothesis, simple hypothesis, when t1 is bigger than 2, right? Or 1.96. That's what we do. So it means that, suppose that the size we like to achieve, our target size is 5%, which is usually the case. So that's what we do when the alpha is 5%, right? It means that the probability of rejecting the null bigger than 2, if the null is true, is about 0.05, which means probability of not rejecting the null is 0.95. So that's the first part in this sequential t-test. Now let's think about the second hypothesis. Let's suppose that this is my null. Again, we are going to do the same thing. We are going to calculate t2 and we reject the null if t2 is big. So you can write the probability again. It means t2 less than 2. And the opposite probability is 0.05. Now that's when you break down this joint hypothesis into a series of two simple hypotheses, right? Now let's think about the joint hypothesis itself. Again, you can ask questions in two different ways. When I reject it, or when I fail to reject it. Okay? When I reject it is harder. It's a probability because there are three cases. So let me ask, when I fail to reject this joint hypothesis, that's easier to calculate because there's only one case to consider. So when you fail to reject, so you're not going to reject this and you're not going to reject this, right? When you fail to reject the first hypothesis, so that's when your t statistics is less than 2. And when you fail the second hypothesis, it's a separate simple hypothesis. That's when your t statistics for the second hypothesis is less than 2. Okay? So the probability of fail to reject the null, if the null is true, is this. Now, this is a probability of A and B, a joint probability, right? Usually very hard to calculate. So to make things simple, let's assume that they're independent. Two events A and B are independent, just to make it easier. Which means that I can break this joint probability into two marginal probabilities. Now what is this? The probability that the first t value is less than 2 in absolute value. 0.95. What is this? The probability that the second t value is less than 2, given that the null is true. 0.95. So what is 0.95 times 0.95? It's about 0.905. 25? So this is the probability that we fail to reject this joint hypothesis, if that is true. So what is the opposite? It's the probability that we reject the joint hypothesis, if the joint hypothesis is true. Okay? So let me write it somewhere. So 1 minus this, which is 0.0975, given that the null is true. So that is the size of the test. And the size is not close to 0.05, it's close to 0.1, 10%. So the moral of this story is this. We initially like to have a test with 5% of the size, okay? 5% of the type 1 error. We end up having a test of about 10% of size. Okay? So the making type 1 error, the probability of doing that becomes double. You intend to make 5 out of 100, you end up make 10 out of 100. It's kind of riskier, okay? So that's why we don't want to do that. So it's confusing, isn't it? So what we can do, if this is the case, there are two options. The first option is harder, so we are not going to do that. The second option is more straightforward. That's why we go with an F-test. So second option is just use an F-test and use the critical value based on the F distribution. It takes care of these kind of issues very naturally. Another, if you really want to use a sequential t-test, then for individual test, you cannot use 2 anymore. It cannot be 1.97 anymore. Okay? So you have to adjust the value here and there. That's typically hard. Okay? So that's why we prefer, at least at this level, to use an F-test instead of the sequential testing idea. Okay, so do you have any questions? It's just correct. So it's a comparison between something wrong and something correct, not something less strict and more strict. Things, okay? Because the sequential t-test does not work. unsophisticated sequential t-test doesn't work. Okay, so let me give another motivation for an f-test. So suppose that you have this model, it's two axes. Suppose that this is your null hypothesis. Suppose that you really believe in your hypothesis. The hypothesis says that x1 is not useful to understand y, x2 is not useful to understand y. So you have to drop them, right? So somehow this model can be viewed as a regression model strictly believing the null hypothesis. Do you see the point? So it's a model under the null. Now one idea to compare these two things, one idea to test this idea is actually compare the R squared. So let's call it an unrestricted R squared, and let's call it a restricted R squared. So this is an R squared of a restricted model. Restriction means you just impose the null hypothesis into the model. Just believe the null hypothesis very seriously and write the model as such. So suppose that this is really true. Okay? x1 useless, x2 useless. Do you expect much change in R squared? It can change, right? But not much. They just stay the same, almost. Suppose that this is false. If you reject it, at least one of the independent variable is useful. Now, what's going to happen to this R squared? It's going to jump a lot, right? Because x1 or x2 or maybe both are useful. So it is going to jump a lot. Jumps like a frog. So this is if null is true. And if this is null is false. So one idea is to make a test based on these two R squared. If the jump in R squared is big enough, you are ready to reject the null hypothesis. Because it means that at least some of them are useful, right? If the R squared is just the same, it's going to increase. Because one thing we learned about R squared is if you add more variable, the R squared only goes up. So what I'm saying is it goes up, but not so much. Okay? So we can imagine a test comparing these two R squared, and it happens that that's exactly the F test. Okay? And I write it as the homoscedastic only F test because that exact relationship is true only when we assume the homoscedasticity. If you assume the heteroscedasticity, then it's more complicated. Okay? So under this assumption, this comparing two R squared is exactly equal to the F test in this sense. So this is the R squared of a unrestricted model, a long model. This is the R squared of a restricted model, a short model. What is Q? Q is the number of restrictions under the norm. Same thing, N is the sample size. K is the number of X in the model, in the long model, in this model. So we have Q is equal to 2, 1 and 2. K is equal to 2. Okay. Now the idea is, if the null is false, then we increase a big jump in the R squared. So the difference is going to be big enough. But the difference also depends on many other things. It depends on Q. If number of restrictions goes up, then the size of two models differs a lot. So difference must be bigger, naturally. So that's why we normalize it by Q. Also, what do you mean by big enough? The jump being big enough. We're going to compare it against something like this. This is a very stable number, so we can use it as a reference, the comparison. Then we can show that this F-test is the same as the F-test I introduced before under the homoscedastic error. And this follows F distribution of Q and infinity. Okay? So we use the same cutoff, same critical value. So one way to run an F-test is actually run two regressions, first and second, save the R squared, and compare them. Okay? But that's another idea. Okay, so let me stop at this point. So maybe tomorrow I'm going to show you how to actually do it in R. And maybe I have another chance to emphasize these small things. Okay, any questions? No? Let's see you tomorrow.